everyone. This side Mansi Mahindru, Assistant Professor at ABES Engineering College. So today I'll take one very important topic of advanced data structure, that is binomial heap. Now let me start. So as it is written here, that a binomial heap is a collection of binomial trees, and each of which satisfies the heap properties. Now we all know the concept of heap. At that time also we have learned that heap basically is of two types. One is min heap and another one is max heap. Now in binomial heap, we are only concerned with the concept of min heap. Now what does this min heap means? In min heap, the key of node is always greater than the key of its parent. Now, let me explain you it with the help of example. Now, for example, if we are standing at this particular node where the key value is 10. Now, here we can see that both of its child nodes, that is 14 and 19, are greater than 10. And similarly, if we are at this particular position, then also we can see both 26 and 31 are greater than 14. And similarly, we have for other nodes as well. So as a conclusion, we can say that if we'll traverse this whole tree, we will get the minimum element, the smallest element of this tree at the root node. So that is the basic concept of min heap, where we'll get the minimum element at the root node, and all the other elements are always greater than the root node. Now, to understand the binomial heap, first, you have to understand what is binomial tree. So now let us learn about the binomial tree. Here it is written that binomial tree BK is an ordered tree defined recursively. So this BK is basically the notation of our binomial tree. A binomial tree is denoted by BK, where K denotes the order of our binomial tree. Now, if the value of K is equals to 0, then our binomial tree only consists of one single node. But if the value of K is greater than or equals to 1, then our binomial tree consists of two binomial trees of the order BK minus 1, and they are connected such that the root of one tree is the leftmost child of the other. What does this mean? What does this statement means? See, as you can see, if the value of K is equals to 0, then we have one single node, right? But if the value of K is greater than or equals to 1, if the value of K is greater than or equals to 1, at that point of time, we have two binomial trees of the order BK minus 1, as you can see, BK minus 1, and another binomial tree of the order BK minus 1. Then how we will connect both of these binomial tree together? We'll connect it like this. See, the root of one tree is the leftmost child of the other. Means one is the root node and another one is the left child of this root node, as you can see like this. So like this, we have to connect these two binomial tree. If you don't understand it till now, we'll take more example, then it will be more clearer to you. So now, as you can see, one second. Yeah. For example, if we'll take the value of K is equals to 0, then it is already written that when the value of K is equivalent to 0, then our binomial tree consists of one single node. But when K is equals to 1 or it is greater than or equals to 1, then we have to draw our binomial tree like this. So we'll take some examples. If the value of K is equivalent to 1, then we have two binomial trees of the order BK minus 1. So here BK minus 1 means if we'll substitute the value of K is equals to 1, then it becomes K minus 1 is equals to B, 1 minus 1 is equals to B, 0. Means for the binomial tree of the order 1, we have two binomial trees of the order 0. So means we'll draw two binomial trees of the order B0 and both of them are connected in such a way that one is the left child of the other. So this is the basic representation of your binomial tree. Now, if we'll take the value of k is equal to 2, then in that case, the value of bk minus 1 will be equals to b1. So here we have two binomial trees of the order B1. So first of all, we'll draw two binomial trees of the order B1. Like this, you will draw. So this is your first binomial tree of order B1, and this is your second binomial tree of the order B1. And both are connected in such a way that one is the left child of the other. So this is the binomial tree of the order B1. And similarly, we can draw it for B2, B3, B4, and so on. Right? Now, we'll take the representation in the form of figures in the next slides. As you can see, when the value of k is equivalent to 0, we have only single node. When the value of k is equivalent to 1, then we have two binomial trees of the order B0 and another one is also B0, and both of them are connected in such a way that one is the left child of the other. Right? Now, when the value of k is equal to 2, then we have two binomial trees of the order B1. And when the value of k is equivalent to 3, then we have two binomial tree of the order B2. Okay, similarly, we can draw for B4 as well. Right. Now, how we can understand it in more simpler terms? So you can see here in the diagram only, we can understand like what is the order of this binomial tree. We'll calculate the degree of each node. See, the degree of this particular node is 0 because there is no further children for this node. So the degree is 0. Now, if we'll come to this particular node, the degree is 1 because there is one children. The degree of this particular node is 0 and degree of this node is 2 because there are two child nodes for this node. So we can say that the root node is of degree 2. So this binomial tree is also of the order B2. And similarly, we can elaborate it for B3. Like you can see here, this particular node has degree 0. This has 1. This has again 0. This has 2. You just have to check the number of childs present for that particular node. This has 0. This has 1. This has again 0. And this has 3. Why 3? 1, 2, and 3. So this particular binomial tree is of the order B3. Okay, similarly, we can draw for B4 also. Yeah. Here I have drawn for all the orders. I have also covered B4. So you can see for B4, we have two binomial trees of the order B3. This is B3 and this is also B3. So we have connected, like one is the left child of the other. And similarly, you can calculate the degree for this and you will get the degree of this particular root node as 4. So we can conclude that this is the binomial tree of the order B4. Yeah, this is another representation of your binomial tree. Like you can say in each binomial tree, for example, if we take the example of B4, in B4 binomial tree, we have the binomial trees in the order bk minus 1 in decreasing order. What does it mean? As you can see here, see, this particular part is of the order B3. This part is of the order B2. This is of the order B1 and this is of the order B0. So in B4, all these binomial trees are connected with the single root node. So this is known as binomial tree. These are just the representations. You can understand in any way that is more simpler to you. You can take it like that, right? See, this is the representation of that way. Like if we are talking about B4, then we have the binomial tree of the order bk minus 1, that is B3, B2, B1 until B0. In the decreasing order, you have to represent. Now, these are the properties of your binomial tree. Now we're going to prove all these properties with the help of example. So we have taken the binomial tree of the order B4 and we'll prove all these properties with the help of this example only. So according to the first property, the binomial tree BK has total 2 raised to the power k nodes. What does it mean? See, this binomial tree is of the order B4. So it means the value of k is equals to 4. So in this particular example, what we will do, we have total 2 raised to the power k nodes. What does it mean? 2 raised to the power 4 means 16. So means this complete binomial tree should have 16 nodes. So let me check whether there are 16 nodes or not. So we'll check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Yes, there are total 16 nodes. So first property is fulfilled. Now, according to the second property, this binomial tree should have the height k. Let me check. This is height 0, this is height 1, this is height 2, this is height 3, and this one is height number 4. Yes, our binomial tree has height equals to k. So second property is also fulfilled. Now there should be exactly KCI nodes at every depth. What does it mean? It says, like for example, if we'll check at depth number 2, so here the value of k is 4 and I is 2, so 4C2. What does it mean? 4 ka factorial upon 2 ka factorial upon 2 ka factorial. So if we'll solve this particular equation, we'll get 6. So we have to check that at depth 2, do we have total 6 nodes? So we'll check 1, 2, 3, 4, 5, and 6. Yes, this property is also fulfilled. Now the fourth property is saying the root has degree k, which is always greater than the other node in the tree. The root has the degree k. Yes, we have already checked it for the other binomial tree also, that if we want to calculate the degree of this particular tree, we'll calculate it like this. This tree, this node has degree 0, this has 1, this has again 0, and this one is having 2, this one is having 0, this one is having 1, this one is having 0, this one is having 3. So here we can say that this particular binomial tree is of the order B3. Now we'll calculate for this also. This degree is 0, this is 1, this is 0, and this is again 2, this is 0, this is 1, this is 0, and this is your 4. This is 4. So the root has degree equals to k. Yes. So all the properties of binomial tree are fulfilled. So we can say, yes, this is the resulting binomial tree. This binomial tree is correct. Each of the root's child is the root of the subtree Bi. It means that all the child binomial trees are in the order Bk minus 1, Bk minus 2, and so on till B0. So all the properties are fulfilled for this particular binomial tree. Now we'll take the actual concept, that is binomial heap. Now what is binomial heap? As it is written, that a binomial heap H is a set of binomial trees that satisfies the following properties. Means each binomial tree in H obeys the min heap properties. As we all know that all the binomial trees are also obeying the property of min heap. So when we'll connect all those binomial tree in one binomial heap, then obviously our entire binomial heap will also fulfill the property of min heap. So this property is easily understood, right? Now, according to the second property, for any non-negative integer k, there is at most one binomial tree whose root has degree k. This property we have also tested here, na? Like one root node should be there whose degree is equivalent to k, right? Now, the binomial trees in the binomial heap are arranged in the increasing order of the degree. It means that whenever we will create the binomial heap for the multiple binomial trees, then those binomial trees should be connected in the increasing order. It should be arranged in the increasing order. First, we have the binomial tree of the order 0, then B1, then B2, and so on. Right? So this is just the representation of your binomial heap. Now, these are the operations that we can perform on every binomial heap. Like we can create our binomial heap. At this point of time, we have just set its head. We have not attached any element on our binomial heap. We have just started creating our binomial heap. Then we can find the minimum element from our binomial heap. We can perform union operation, means if we have two separate binomial heap, then we can merge those two binomial heap as a resulting one heap. We can extract the minimum element from our binomial heap. We can insert any new node in the binomial heap. We can decrease the key of any node from the binomial heap, and we can delete any key as well. Now, so in this particular video, we're going to cover make heap operation. We're going to cover the second operation, that is finding of the minimum element from the binomial heap, and rest all operation we're going to cover in the subsequent videos. So the first operation is make heap operation. In this operation, we have just started with our binomial heap creation. We have set its head pointer, and head is still pointing to nil because there is no element connected to binomial heap. So here head h is equals to nil. Okay, we have only started with the creation. So the running time complexity of this particular operation is obviously O of n, O of 1, sorry, because still there is no element on which we can perform any operation. Now the second operation is minimum edge operation, means we want to find the minimum key from our binomial heap. So how we will going to find it out? So this is the pseudocode that we have to follow to find out the minimum element or the minimum key from our binomial heap. This is our pseudocode, and we're going to dry run this pseudocode on this particular example to make it more clearer. So let me start with the dry run of this pseudocode. So as the first line says that y is pointing to null. So means this head pointer, we can say it is as our y. X is pointing to, now head h is pointing towards x. So head h is pointing towards x. So this is our x. Min is set to the default value equal to infinity. So we'll set min is equals to infinity. We all know that any value will always be smaller than infinity. So we'll set it to the larger value, that is infinity. Now this loop will run till the x is not equals to null. Okay. Now, if we'll start with our loop, the first thing that we have to check is the value of key of x. Now here the key of x is equal to 20 and our min is equals to infinity. So obviously 20 is less than infinity. So what we can do is we can update key of x to minimum. So we can update our min from infinity to 20. We have updated it. Now what it is saying, it is saying just change your x to y. So you have to change your x to y. Now this becomes your y and sibling of x becomes your x. Now the sibling of x is 15. Now it will become your new x. Again, x is not equals to null. So you will again dry run this loop. So here the key of x is 15. The minimum is 20. 15 is less than 20. So you'll update your minimum to 15. Again, you will change your x to y. So this becomes your y and sibling of x becomes your x. Again, you will check the key of x is 8. Your minimum is 15. Yes, 8 is smaller than 15. So you will update your minimum. So it becomes 8. Then again, you will change your x. Now this becomes your y. And it is saying that sibling of x becomes your x. But sibling of x, sibling, there is no sibling of x. So you will come out of the loop. Here x is equals to nil. So you'll come out of the loop and you will going to return the value of y. What is your value of y? Y is pointing towards 8. So you will return y is equivalent to 8. So as you can see, the minimum element present in this particular binomial heap is 8. So with the help of this pseudocode, we can find the minimum element. Now, the next task that we have to perform is to find the time complexity of this particular operation. As you all know that in the binomial heap, it follows the min heap property, means all the minimum elements are present at the root node only. So we don't have to traverse the entire binomial heap. We don't want to traverse this particular node. We don't want to check for this path. We just have to traverse the root nodes, because we know now each of the binomial heap, each of the binomial tree is having the min heap property. So the minimum element is present at the root node only. So this particular operation will only take log n time. So the time complexity for this particular operation is O of log n, right? And according to the properties of binomial heap, we have also learned that the binomial heap, all the binomial trees should be arranged in the increasing order. We also have to check that property here. Let me check it. See, this particular binomial tree is of the order B0 because there is no child node, so degree is 0. This particular binomial tree is of the order B1 because it has one child node, and this particular binomial tree is of the order B2 because there are two child nodes. Yes, our binomial trees are arranged in the increasing order, so we can say, yes, this binomial heap is fulfilling all the properties of the binomial. So these are the references. Thank you so much. All the remaining operations that are left, that is union, decrease key, delete, extract, minimum operation, that we're going to take in the subsequent videos. Thank you so much.